Good evening, everybody. So, in this lecture, we will discuss on the flow around submerged bodies or the flow around the immersed bodies. When the flow takes place on an object or a body submerged in the fluid, this body is subjected to two forces under a defined circumstances. And those two forces are the drag force and the lift force. And these forces are very, very important. And let us now work on these when they will be introduced or when they will act. And if they act, why the force or what is the reason for the force, to be frank, and how to really analyze them. So these are the things which we will study in this particular lecture. Let us straight away go into the lecture. When an object is placed within a fluid stream, this is what we are studying. When an object is placed within a fluid stream, just not fluid, fluid flowing with some velocity v, a force is exerted on the object that may be inclined to the direction of the flow. A force is exerted, and which is that force is in the inclined direction. This force is due to viscosity of the fluid and there are two reasons. One is viscosity of the fluid and the pressure distribution. This is the second reason. The pressure distribution over the body surface. Over the body surface. These are the two reasons why basically that force is coming into picture when a object is submerged in a body and this fluid is now flowing. So in a flowing stream, we have basically kept an object submerged in that, and this body is subject to a force, right? And that force will be inclined to the direction of flow, right? And this force actually is why this force is there. One reason is the viscosity of fluid and the other is how the pressure is distributed over the body surface, right? Next, this is second point. Third point, actually, the component of this force, the component of, because and I mentioned the force is in the inclined direction to the flow, basically the component of the force parallel to the direction of flow, parallel to the direction of flow is called drag. Similarly, the component of force, the component of the force normal to the direction of flow is called lift. Two components I introduced to you. One is the drag, the other one is the lift. And now in many engineering problems, in many engineering problems, basically, we need to determine, we need to determine these forces, these forces basically. Why we need to determine this? The wind pressures on the buildings. That is one application. Then basically d- different, basically different. So rather than different, I can different. Okay, different body shapes in the case of automobiles. We need to study right now. This is one application. Similarly, the body shapes already I told that body shapes may be automobiles. Again, that body shapes may be of aircraft. It may be body shape of a propeller, for example. Maybe basically what you call it as any rotating fans. So all these basically we need to study. Why? Because to determine the efficient shapes. What do you mean by that efficient shapes actually? Least resistance. Drag force is minimum. So this is the object of the study. Actually, in all these cases, actually, when we are doing it, how basically the whether the drag force can be minimized by changing the body shapes, irrespective of whatever you are taking an automobiles, you may be taking an aircrafts, whatever you take it, or you may be taking turbine basically, or you may be taking basically the centrifugal pump blades, whatever way, in every application, in order to reduce what you call it as the resistance, naturally this we will do it in the analysis of these problems, basically whether the object moves through the stationary fluid or basically the object is stationary in a moving fluid or the object is moving through a stationary fluid, anything is happen. For example, now if you take it an aeroplane is basically moving through a stationary fluid. So that is then this object aeroplane is subjected to some resistance, and that resistance forces are basically parallel to the direction of what you call it as the air flow. The aircraft is what because object is now moving, so now it parallel to the direction of it is the drag force, and perpendicular to the direction of it is the lift force. So now our objective is how to the minimization of the drag force through choosing an efficient shape for the wings of the aircraft, for the nose of the aircraft. So how we can shape the aircraft body so that actually the resistance force is minimum. And this resistance force reasons are what? Number one is viscosity. Number two is the pressure distribution. So now we will study into that slowly, one after the other, right? So now if you understand this, let me go into the lecture actually. An insight into the actually into can be right. An insight into the phenomena of the drag and lift can be obtained by considering right, by considering the flow pattern around an object. Just imagine that the aircraft is submerged in air. This is the thing that you take. Now, basically, how we explain the drag and lift there. When flow occurs about an object, when flow occurs about an object which is either unsymmetrical or axis not parallel to flow, right? Flow direction. So naturally, object always will not be parallel to the direction of the flow. So it may be in inclined direction. Why I tell unsymmetrical means it is not symmetrical to the flow direction. It is unsymmetrical to the flow direction. That you should understand. So in such a case, what will happen actually? In such a case, actually, in any of these things, the flow around will be unsymmetrical, causing local velocities and pressures on either side of the body. On either side of the body. This is what happens actually, right? So now what happens? Basically, the pressure difference, because now I told that the pressures on either side of the body. So the pressure difference actually over the surface, the pressure difference over the surface causes a net force to act on the body. This is one reason. Next, in addition to this, basically, in addition to the pressure difference, actually, right, there will be another force tangential to the body due to viscosity. Due to the viscosity, basically, which we call it as the viscous force. So that means the forces are due to two reasons. Due to the pressure difference over the surface of the body, that is one reason to cause a net force to act on the body. That is first reason. Second thing is due to the viscosity of the flowing fluid. Actually, the viscosity of the flowing fluid, there will be a force tangential to the body, which is nothing but the viscous force. These are the two forces, and these two forces together cause actually the drag and basically the lift. That is what I wish to convey. These two forces together will cause actually the drag or lift. For example, now consider a body held stationary. Now, just for explaining, body is held stationary in a real fluid. I mean by real means the fluid is having some viscosity. In a real fluid which is flowing at a velocity, right? V, which is called as uniform velocity, right? At a uniform velocity, V. Right now what I have taken a shape, you see it, just for explaining. So this is the body, you take this as the body which I have taken, right? If I draw the axis of the body, this is the axis of the body, axis of the body. Now perpendicular to the surface or axis of the body, this force will be acting actually, right? So now if I take it, basically the one is parallel. Now the how the flow is taking place, this is basically the stream flow. This is how it is at the velocity v, uniform velocity. So now if I take it parallel to this stream, if I take it, this is what we call it as drag force, and perpendicular to it, if I take it, this is called as lift force. So kindly remember, the fluid exert a force, just again repeating, on the stationary body, right? The total force F is perpendicular to the surface of the body. The total force is in inclined direction. That's what I have drawn. This force can be resolved into two components. One in the direction of motion, the other perpendicular to it. The component of force, this is resultant force. I better call it as FR. Even the figure also you can write it FR. I mean by resultant force, FR, in the direction of flow, or in the direction of flow, is drag force. The component of the force, therefore, perpendicular to the direction of flow or motion, whatever it is lift force. I have shown there also how the drag and lift will be actually. So both I have shown. Lift force comes into picture only if the axis of the body is inclined to the direction of flow. Suppose if the axis of the body is parallel to the direction of flow, then lift is equal to 0. Only if the body is inclined, there will be lift. If it is horizontal, parallel to the direction of flow, then lift is equal to 0. In such a case, in such a case, there will be only drag force. Next, if the fluid is ideal, please remember, very, very important. If the fluid is ideal and the body is symmetrical, symmetrical examples are, for example, a sphere, a cylinder, both drag and lift are 0. The reason being, if it is ideal, viscosity is 0. So the naturally the force due to viscosity is 0. If it is symmetrical, actually the pressure distribution is such that there is no pressure difference at all. Unless pressure difference is there, then naturally that resistance force will not come into picture. So when there is no pressure difference in the symmetrical thing, basically, so that is why the resistance due to pressure difference will not come into picture. Therefore, drag is 0, lift is 0. So kindly remember, we not in what circumstances there will be no drag and lift. Number one, fluid should be ideal fluid. Number two is the body should be symmetrical. So in such a case, there will not be both the things. So now let us, what is the expression for drag and lift? Just I will explain what it is also. For example, take an object. If I take an object just like this, so how you anything you take it, but they better not take it. Say it because it sends wrong signals. If I take a what you call it as a spear-like thing, so I take some other shape just for your understanding sake, like this. Just so if I take like this, now I consider any some small area here just for analysis, right? You know that basically the resistance will be Fr will be like this. So naturally Fd will be like this and this will be Fl for us. This is what the process is. Now, actually, how this I told what are the two things I told. One is pressure difference actually. Second one is what you call it as the viscosity. So this is the region pressure distribution and viscosity means viscous s- stress or force. Right now, if I take it, how the pressure will act? Pressure will act normal to this always. Pressure always acts normal, whereas the shear acts tangential to this. This is how the shear will be because shear is something tangential to it. So this is how it will act. If this is small area dA, the shear force is tau naught into dA tangential to this area, whereas pressure is always normal to the area. This is how these two acts. So what I have taken, I have taken a small area like this, right? If I now see the forces actually, so how the forces are, number one is tangential to it is the shear force and perpendicular to it is the pressure force. This is how actually. Now I want to analyze. If I analyze it, if I take actually suppose the horizontal if I take it, so naturally if this angle I call it as theta and this is you know it 90 degrees, so naturally this will be 90 minus theta, right? Now let us analyze the forces. For example, right, what we mentioned, now I take the total drag force. Total drag force, if I take it, that I call it as Fd. If I take it, now what is it? Now what should I take it? It should be the sum of basically the dis- pressure distribution component and the shear stress component parallel to the direction of motion or direction of flow. What is the, now you take it, the pressure component in the direction of this. So now if you take it, this is it, what is its component in the basically if I take it in the parallel to it, if I take it, then it will be basically PDA into basically cos theta, right? This is PDA cos theta, right? Now, integral of it, it will give total over the entire area. First, I have taken only component here, then total if I take it, then plus integral. That means total I am taking integral tau dA, right? If you take it, tau dA, basically, what is the thing? Cos 90 minus theta, that is sine theta. How sine theta has come? Now you see this is 90 minus theta. So now you take the in the x direction. So tau dA sine theta integral will give you some. This is what is the total drag force. Similarly, what is the total lift force? Now I have to take it in the normal direction. If I take it in the normal direction, same sum if I take it. Now just see it actually how it will be. Suppose if I take it, now pressure is acting in this direction. So if the pressure is acting like this, so this is the component, this is the other component. If this is PDA, now this is PDA cos theta because this is theta, and this is PDA sin theta. This is how we need to calculate. Similarly, even the this one you take it, for example, shear if you take it. So this is how the shear will be. Actually, this is tau naught dA, right? And this is 90 minus theta, right? This is normal to it. So naturally, this is theta. If I take it here, it will be basically tau naught dA cos 90 minus theta, that will be equal to tau naught dA sin theta. Whereas here, if you see it, so if that is the case, then basically how it is acting. So the other one is acting, sorry, this is how it acts. So now what I should do, if this is 90 minus theta, this has to be theta. So how it will be? It is tau dA cos theta. So now the directions also see it. Whereas pressure, if you take it, both are in the positive direction of x-axis. Whereas if I take the vertical direction, pressure is acting downwards, shear is acting upwards. That you should remember. When it is acting downwards means naturally I need to take it as minus. Minus integral PDA, basically it is sine theta. Why minus I have put? It is acting which direction? In the downward direction. Plus actually integral tau naught dA cos theta. So this is the next one. Or simply we can write this integral tau naught dA cos theta minus integral PdA sin theta. So this is the expression. Now if I want what is Fr is equal to, Fr is equal to, if I want, I can calculate this. But now this analyzation of it is very important. I have given you the equations, okay, for drag force. I have given drag force, basically the drag force, which is equal to what I call it as integral pre dA cos theta plus integral tau dA sin theta. How to analyze it? So that is how the equation given to it is CD into basically area into basically rho v square by 2. This is the equation for drag force. Similarly, lift force FL is equal to CL into A into rho v square by 2. Now if I see this, everything is now basically fixed in these two. So determination of these two are the whole crux of the topic. That is now beyond the scope of yours, because only for us just to understand what is drag, what is lift is our objective. But just equations are very important. So kindly remember it. This is the drag coefficient. This is the lift coefficient. How to calculate the drag coefficient? What are the equations for the drag coefficients? That is all different story, which we don't work right now. And if you want the resultant force, F is equal to square root of Ft square plus Fl square. Now our main topic here is only to understand what is drag force, what is lift force, when which one is dominant. So now actually finally what we have find out is what is the total drag force if I take it. So Fd is equal to, you must have seen, it is integral PdA cos theta plus integral tau naught into dA sin theta. There are two components. This is first one, integral PdA cos theta is called as pressure drag, or this is also called as form drag. Please remember the terminology. and this is called as the shear drag. This is also called as friction drag. Friction drag, shear drag, all are same. Or this is also called as skin drag. So this term represents pressure drag. This term represents the shear drag. So now let us say what is the relative contribution of pressure drag and shear drag basically to the total drag, to the total drag. It depends on three things actually. One, it depends on number one, shape of the immersed body. This is number one. Number two, basically, is position of the immersed body, shape of the immersed body, position of the immersed body, and third one is fluid characteristics. So these are the things which will define which drag is important, whether pressure drag is more or friction drag is more, or pressure drag is less or shear drag is less. Which one is relatively thing? So I will show you the examples also. For example, let us take one first one actually. I have taken a plate like this to understand only what is the relative contribution of the things. Now this is how the flow will be. So now I have kept actually first case one, if I take it actually a flat plate I have taken. Now the flow over it. So flow over a flat plate, right? And how this plate is kept actually parallel to the direction of flow. This is how it is kept. Now, when I have kept it actually like this, right? Let us say this is a velocity v. What will happen? Only parallel to it, right? Not this direction actually, sorry. The direction. So now flow is taking place, body is here, now it is moving. So naturally, when it is applying, this is the force. This is shear, right? This is how it will be. Then naturally body is kept like this. So that means if a body is kept like, you remember, if this is how the body is, right? Generally, if the body is like this, then we have taken it as, now you remember, this is how the pressure acts and how the shear acts. This is tau naught, this is pressure. That's how we have taken. Now it is completely now like this. So when it is like this, flow is like this. What is happening actually? The pressure acts normal to the plate. Am I right? See the direction. Why? Because theta is equal to 90. There. Where then in that case, what is PDA cos theta becomes actually, so PDA cos 90. So what will happen? You see 0, right? Whereas here, then in such a case, total drag is equal to only shear drag. So here the pressure drag is equal to 0. Suppose now I keep basically a body flat plate perpendicular to the direction of flow. This is how I have kept. Right? Now this is the flow. The velocity v. How the flow takes place, if I see the flow lines, if I draw, this is how the flow lines. This is how the flow lines. So this is the plate. This is upstream. This is downstream. If you see, there is a pressure difference between upstream and downstream that results in basically the resistance here. And this zone is called as wake. Right? The pressure is so low here because of the high pressure difference. Actually, the force is coming into picture. In such a case, if I take it, this is how the shear acts. Right? In such a case, what will happen? Theta is equal to 0. When theta is equal to 0, this is case 2. I took case theta is 90, first case. Theta is equal to 0. In such a case, actually, tau naught into dA sine theta is equal to 0. That is, shear drag is 0. Therefore, total drag is what? Only pressure drag. I took two extreme cases: body parallel to the flow, body perpendicular to the flow. Body parallel to the flow, the whole thing is due to shear only. So the total drag is shear drag. Body perpendicular to the flow, there is a pressure difference on upstream and downstream. So the total drag is due to only the pressure drag. The shear drag is 0. So now naturally, if you keep it in the inclined position, now both will act. That is the thing. If suppose extreme is theta is equal to 0 vertical, when theta is equal to 0 vertical, you keep it, then in such a case, pressure difference. Pressure difference means shear drag 0. Theta is equal to 90. So that means parallel. When you keep theta is equal to 90, again extreme case. There actually what will happen? The pressure difference is 0. So the total drag is shear drag. So theta to 0 to 90, if you're taking, then there will be in between, if you take it, both will be contributing. So that is what you should understand, how what is the relative contribution of each of these things. Now next, one important topic I will tell you, what is the difference between the streamlined body. What do you mean by streamlined body, bluff body? These are very, very important. Sorry. Streamlined body, bluff body. This is BLUFF. So what is streamlined body means actually? Now I will show you. The airfoil shape, the bird foils. You take it. This is the airfoil. This is the airfoil shape, right? Whereas the bluff body means blunt body. So blunt body means this is how it will be. This is the blunt body or bluff body. What is the difference actually? Streamlined body is that body which is such that the shape is adjusted following the streamlines. Now the flow, you take it, how the flow occurs. So in such a case, the flow lines just move on the object like this. Right? So in such, this is airfoil. So here where the pressure difference is a bit almost closer. Here only the wake is formed. That means wake is a very, very low pressure zone. This is formed here. Right? So if you draw the streamlines are nothing but the flow lines. The flow lines flow over the body like this. And in such a body, what is the advantage is naturally the flow will never get separated. Please remember, the flow will never be separated. This is one thing you should remember. So, once again, this is what I call it as the streamlined body. Streamlined body means shape, you see it, airfoil shape. So now flow over it. If I take it, this is the flow direction. How the flow will be, right? The flow will be such that there will be no separation at all. In the bluff body, you take it, if the flow lines will be like this, the flow lines will be like this. So that means the flow line is getting separated here itself. So this is one streamline, this is another streamline. So the remaining streamlines, whichever they flow, they will be stopped here. This is how it will be. So now here it is the wake because of the pressure difference. So this is called as a low pressure zone. So because of this low pressure here, there is a large pressure difference on upstream side and low. So this pressure here is high pressure. Here, low pressure. So if this is like this, we call it as a bluff body or blunt body. Here, the body shape is streamlined. Then naturally, this is in such a way that streamlines follow this body. Then actually, what is the use of it right now? What is a streamlined body? Streamlined body is defined as Streamlined body is defined as the body whose surface, please note that whose surface, because what I have drawn, whose surface coincide, coincide basically with streamlines. This is called as streamlines when the body is placed in a stream. Right? This is as far as the streamlined body is concerned. Now, if I go the other one, what you call it as bluff body, then a body whose surface does not coincide with streamlines when the body is placed in a stream. Right? So what will happen? So if it follows the streamlines, streamlined body. If it is doesn't coincide with streamlines, it is bluff body. So now what is the problem actually? So whether it is streamlined body or whether it is bluff body, what is the problem for us? So in the case of a streamlined body, because the body shape is such that it coincide with the streamlines, right? Separation will be only the separation occurs only at the trailing edge, almost at the end. And next, even though The boundary layer starts from, even though the boundary layer starts from leading edge, even though the boundary layer starts from the, it will not separate, will not separate till the trailing edge. Here, the wake zone at the edge where separation occurs, wake zone is very small. Right? Wake zone is very small means basically that means the pressure drag is very small. Pressure drag is very small, almost negligible. So when that additional component, that pressure drag is completely not there, then in the streamlined bodies, in streamlined bodies, total drag is equal to only friction drag or shear drag. Now if I go to the other one, here the second one. Now what happens here? Flow separation occurs. Occurs. Flow separation occurs where? Very, very nearby. Flow separation occurs actually here from the surface of the body. Flow separation occurs from the separation of the body. That means because of that, actually, a large wake zone is formed. Right? Here, the pressure difference, the pressure, the drag force is due to the drag force is due to pressure, and it will be large compared to shear drag. So that is why basically we never try to keep a bluff body. We always make a what you call it as the shape of the body as a streamlined body. Right? This is one of the things. So that there will be no pressure drag at all. It's only shear drag. So if we design it for that, fine. Whereas in the case of bluff body, the whole maximum pressure drag will be there, and always the magnitude of the pressure drag will be much, much higher compared to basically the shear drag. Here one more also, which is very important for problems. What is the terminal velocity? A bit question actually of a body. Terminal velocity thing. It is the maximum, it is the maximum constant velocity. The maximum constant velocity of a falling body. Right? Maybe a spear or mainly parachute. That is one of the very, very good example. Parachute, right? With which, with which the body will be traveling. The maximum velocity actually. So at terminal velocity, the condition is the weight of the body W is equal to the drag force plus the buoyant force. Kindly remember, this is the weight of the body is equal to, this is the drag force and this is buoyant force. So kindly remember. And one more last point is, what is Magnus effect? So the Magnus effect is when a cylinder is rotated. Please note, when a cylinder is rotated in a uniform flow, when a cylinder is rotated in uniform flow, a lift force is produced on the cylinder due to the circulation. And this phenomenon of lift force produced by rotating cylinder in a uniform flow is known as Magnus effect. So this is one of the important things. So that means, for example, if I take it last only how to show that. Now this is the cylinder. If I take it, what will happen if I take it this cylinder? Now this is S1, S2. They are called as separation points. Now this cylinder is rotating. Now the flow is like this. This is how the flow lines are. So here, if I take it, this lift for L, or this is called as lift. So in this direction, suppose if I take it, this is X direction. So this is Y direction. So this lift produced in this is what we call it as, this is the rotating cylinder. The rotating cylinder in a uniform flow experiences a lift, and that is what we call it as Magnus effect. I will stop this lecture here and let us discuss in the next class the problems on this and how to go about it. Thank you very much. Thank you so much.
Like, share, and subscribe. Hit the bell icon for more updates.